Hello, this is Warren Powell. Welcome to part 4 of my talk on the Universal Modeling Framework for Sequential Decisions. This is on designing policies. Now, I'm often asked, what is a policy? A policy is a method that makes a decision using the information in the state variable. Any method. Now, I'm up to almost 50 different ways in the English language with words that effectively mean, in this right context, of how to make a decision. So this is something that's pretty widely understood and applied within the English language. Now, there are two fundamental strategies for designing policies. The first of these, called policy search, is to design functions that work well over time. Now, these functions do not plan explicitly into the future. We just train them to work well over time. Whereas the second ones, the look-ahead approximations, do explicitly plan into the future. Each of these will be divided into two classes, creating 4 classes of policies. The policy search class begins with policy function approximations. So these are analytical functions that specify what to do given what we know. Order up to inventories. Buy low, sell high. If it's cold, wear a coat. We might use large language models trained to diagnose patients. If they have these attributes, use this medical treatment. PFAs are lookup tables, they're linear, nonlinear models, they're neural networks, any function we might use in machine learning. Of the 4 classes of policies, this is the only class that does not have an embedded optimization step in it. Now, the second one, cost function approximations, does have an optimization step. We're going to start off where X here is a choice. It's a discrete choice, maybe choice A through choice G. And each one has an estimated performance, an estimated value, but I don't know exactly what it is. And then I have some sort of uncertainty bonus, something that's proportional to my level of uncertainty. Now, one way of solving these problems, and there's many, but a way of solving these problems is to take the estimate plus the uncertainty bonus, add it into a single index, and find the maximum. That's an optimization problem, okay? And so I find the best of these. It's a sort. It's not a very complicated optimization. Everybody's done this at one point. Now, this is easily the most common decision problem that all of us run into in day-to-day life. Now, it's one thing when X is some sort of a discrete choice. It's completely different when X is a vector. So maybe I have a set of machines that I have to assign to tasks. And the X's are the black lines. They're all the permutations and combinations of how I can assign machines to tasks. We write this in this way of math programming, well understood by people with that training. Now, this is a static problem. In reality, I'm going to solve this repeatedly over time. And usually what people do in practice is they throw in bonuses and penalties and whatnot to make it work well over time. And it's very ad hoc, but it's common practice. In fact, it's widely used in industry. Airlines optimizing schedules, they put in schedule slack so that the planes are not consistently arriving late. Manufacturers have buffer stocks. I came up with this idea watching grid operators where they plan how much electricity generation capacity to plan for tomorrow, given that generators might fail. And I realized that although what they were doing sounded very ad hoc, I decided, no, this is actually a really good idea. And what they were missing was having fancy names and fancy math. So now let's go look at the look-ahead approximation. So I've done the 2 classes of policies for policy search. The look-ahead approximations is where I actually have to plan into the future. So this is my slide of Dorothy and the Wizard of Oz, and she's trying to plan her trip to Oz, and she has to decide which turn to make, but she has to plan into the future. So, for example, let's say I have this plant down in Mexico and I have to ship inventories to distribution centers, but I don't know what's going to happen after that because then it depends on what the warehouses and customers order. So I'm going to make an initial allocation so I know the cost of sending it to the distribution centers, and then I'm going to have these downstream value functions. And these curves say, here's the value of having this much inventory at each of the distribution centers. And now when my manufacturing plant makes the decision, I'm going to strike a balance between the initial decision and the downstream value. So those VFAs are capturing the future. And when these work, it's a very powerful way of solving problems, but it's not the easiest method to apply. And often what we end up doing is the fourth class of policy. I like to describe this as what we do when all else fails. So I'm going to illustrate this with my favorite example. I'm in Hartford, Connecticut. I'm working with Pratt and Whitney at the time, and maybe it's 4 o'clock in the afternoon, and I have to plan my route back down to Princeton in the lower left-hand corner, and there's Google Maps saying, oh, here's this great path right through New York City. Now, this is a direct look ahead. I'm planning into the future. I'm planning my path all the way to Princeton, but I'm ignoring uncertainty. But me as a user, I can look at it and say, well, wait a minute, that's a very risky path. And what I may do is, because of the risk, I'm going to route around it. Now, what I have just done without any math or computers is I've used a concept called robust optimization. I took the worst case and said, what's my best decision given the worst case of each of these routes? Now, there's various other strategy, decision trees and approximate dynamic programming and stochastic programming. I mean, here's 5 entire books on how to plan into the future, 4 of them where I explicitly account for uncertainty as I plan into the future. Now, let's consider this article from the New York Times in 2021. So when you have an inventory-based business, most people think only about the first order. With long lead times from the factory in China, he was almost immediately trying to figure out how big his second and third orders should be. Underestimating would hurt not just the sales, but the overall status of his Amazon listing. Overestimating would drain him of cash, and he would incur further charges from Amazon from storing excess inventory. So he has a real overage-underage balancing problem. Now, what he's doing is he has this decision, and he has to figure out what the order is, but now he has to deal with the uncertainties of what the sales would be and the shipping delays. Now, what he was talking about is he has to think about the decisions in the future, his future orders, which also have to consider downstream uncertainties and so on and so forth. This is effectively what he was doing. He was doing a stochastic direct look-ahead policy. Now, I have just covered 4 classes of policies, the 2 under policy search, the PFAs and the CFAs, and the look-ahead policies, the VFAs and the DLAs. Now, we have seen all 4 of these being used. I claim that we humans, with no technical training at all, will use each of these 4 classes of policies in the right setting. Somehow our brains just know how to do this. What's hard is teaching a computer how to do this. Now, of the 4 classes of policies, 3 of them involve solving optimization problems. And this can get very confusing. So if you have a policy that does not involve solving some sort of an optimization, even if it's just a sort, okay, then you have a PFA. But if you are solving optimization, you could be in any of the 3 classes or a hybrid. Now, my big claim is that these 4 classes of policies are universal. They cover every method for making decisions for any of the 6 types of decisions. It covers every method described in the literature or used in practice, even methods that haven't been invented yet, because these are meta-classes. What it means is that you're already using one of these 4 classes and maybe a hybrid, and you can put together hybrids. And by the way, we humans routinely do it, where sometimes we'll plan into the future a couple of steps and then use a VFA. So this is all very standard. Here's a little example of managing a wind farm where I can get energy from the wind farm that's highly variable, but it's free. Or I can back up and get energy from the grid where, let's say I have an infinite supply, but the price of electricity on the grid is highly variable. Now I'm trying to meet a fairly predictable load in this building, and I have a Tesla Megapack battery storage device to help smooth out the fluctuations. So we put together, I was working with a postdoc at the time, Stefan Meisel. He's now a professor at University of Twente, and Stefan did a fabulous job. We created, for this wind farm problem, but we created 5 variations. Now, we created the variations recognizing the strengths and weaknesses of each of the 4 classes. So we have 4 types of policies, 1 from each of the 4 classes, and then a 5th policy that's a hybrid, and we made each of them work best. Okay, so this is a message that says you have to know all 4 classes. Now, so this is sort of emphasizing that we really need to teach students the full toolbox. Now, how do you evaluate performance of a policy? So, well, number one is you simulate it on the computer. This is what I used to do as an academic. These are often referred to as digital twins. Here's a simulation of Pratt& Whitney. It's a multi-agent simulator. We have parts coming from all over the world. Here's another simulator I'm very proud of. I built this at the university, but it's now used at Optimal Dynamics. Every time we land a carrier, we calibrate this, and we have an automated process. It's really quite amazing, where we will calibrate this for each new customer. And that way we can do testing for the customer using this simulator. Now, there's going to be a lot of times where we just can't build a simulator. These things are time consuming and expensive, which means we're going to build the policy and then just put it right in the field. I call this learning while doing. And this is how most testing is done. It's slow. It's not useful for simulating rare events, but it avoids all the complexities of modeling complex dynamics, which really can get quite hard. Okay, I'm going to now stand back. So we've got our 4 types of policies. I'm going to split the 4th type into 2 classes. One is deterministic look ahead, where I plan deterministically into the future. I assume I have point estimates of everything. And the other is where I do model the uncertainty. For the one where I do model the uncertainty, I'm going to further divide that into 2 classes. One where the decisions are some sort of discrete set, ABC, and the other is where the decisions are continuous and or a vector. Okay, so now I have 6 types of policies, and I can ask the question, which are the most useful? Now, this is not something you get out of a textbook. This took a career to do this, but here's the answer. I have divided the policies into 4 categories. Now, category 1, hands down, the most useful. We all use these 3 types of policies: the PFAs, the CFAs, and the deterministic DLAs. Okay, widely used. Every human does it, even if you have no training. Anytime you ever have to make a decision with a computer, you're going to be drawing on these. Now, sometimes I really do need to look in the future and anticipate that there is uncertainty. If I have discrete actions, that's called decision trees. And we teach that to business students. It's fairly widely done. It's not like the average man on the street knows what a decision tree is, but many, I'm going to say almost all business students have heard of decision trees, because looking ahead with uncertainty is very common in decisions. Now, category 3, we take a big shift downward. This is where things start to get complicated. And I know about this category. I spent 15 years of my life, and I have a 600-page book on this category. So this is where we use value functions. This is where we take a step out and then use a value function to capture the future. And I describe this as a very powerful strategy for a very small number of specialized problems. The academics love this category, but it's not that widely used. Even worse is category 4, where I do a stochastic look ahead for vectored valued problems. This is something that Danzig pioneered, and there's thousands of papers, and just not very much of this is being used. Now, choosing policies is a lot like choosing a statistical model. So we saw these 2 functions before, and we want to do demand as a function of price, and somebody can come in and say, oh, I just think a line will do, and somebody will say, no, it's got to be an S-curve, and we can debate these. This is roughly how we go about designing policies. There's a certain amount of human input and subjective judgment. Now, I like to think of these functions, whether it's a statistical function or a policy, like cars. So we all know about cars, and we know what they do, we know what they're good for, but we don't necessarily know how they work. We don't know how the electronics work, we don't know how engines work, but we do understand the technology. And I think that we have to get to the point where even if you're not mathematically inclined and you have the skills in the analytics, you should still have an understanding. And those of us in the analytics space need to start learning how to explain our analytics comparable to the level of skill that you need in understanding a car. Now, let me compare machine learning to picking out policies, the parameterized policies. So in machine learning, I have to choose a function. And again, we're going to generally be using a human to say, what is the best type of function for this? But then we're going to use the computer to do any parameter tuning, and we're going to do that using a training data set. Now, parameterized policies, let's say we just take those in category 1 and they each have tunable parameters. Choosing which to use are the PFA, CFAs and deterministic DLAs. Generally, it's going to be done by a human. Now, for the rest of it, we're going to need a system model. We don't use a training data set. We have to model the physical problem. And then generally these policies have tunable parameters, and we need an algorithm to do that. Now, this is hard, but the process is basically the same as machine learning, and we need to think of it in these terms. Now, how do you evaluate policies? Well, I'm up to about 6 different dimensions. Of course, we want to know how well it works on average, but then we want to know the worst case because they don't always work equally well all the time. Computational, how long does it actually take to compute? Because some of these policies are slow, but how well it works on average, fine, but sometimes there's a long tail. Transparency, do I understand how it made the decision? Because that has to do with the dependency on data. How flexible is it? How complex is it? How hard is it to develop? And what are the data requirements? So this is where I like this little cartoon, because the academics love talking about optimal policies. And I'll be honest, I don't really know the meaning of optimal. We certainly do care about solution quality, but we also care about all of the other metrics. I like to emphasize it's not what tool you use, it's how you use it. You can use a simpler tool that doesn't model stochastics as long as you recognize that it's going to be going into an environment where there is uncertainty and things are going to be changing. Thank you very much. That is my part 4 on policies. Even if you're not going to end up having to program policies, what I'm doing here is indicating that there is a general framework for making decisions, and so you don't have to think about how to make decisions when you're doing the framing. Just figure out what decisions you need to make and get to the design of the policy later.